This is the exam one study guide review video. So what I'm going to do is I'm going to go over each point in the study guide, give an explanation of kind of what to look out for. I also want to keep in mind, want you all to keep in mind some different tools that you can use to study for this first exam, as well as provide you just an in-depth or in detail of what the exam is actually going to be like. So I'll start with what the exam is going to be like and I'll work from there. So it's going to be 50 questions, all of which will be multiple choice. They do come from a test bank, so no two students will get the same exam. However, as far as the topics being covered in those 50 questions, whichever test or whichever questions you get from that test bank will be on any of the topics that are in our study guide. Fair enough. You'll have one attempt. I will post it, and you'll have one attempt to complete the exam, and that one attempt will be an hour and 50 minutes. So be sure that you set aside that at least 2 hours to take the exam. In the duration of time I provide, about 2 days. I'll post an announcement stating when the exam will go live, and you can read all the information there as far as how long you'll have to take it. But I'll post that announcement the same day I publish the exam, which will be this week. So, yeah, as far as what you can use to study, oh, and it's an open note test. I need to state that as well. It's open note. Now, as far as what you can use to study for the exam, any in-class activities we've done, if you have received feedback from me on those activities, then that's feedback that you can use to study to better your understanding of the topics covered. If you did not receive feedback on an activity or homework works the same way. If you didn't receive any feedback from homework or an activity or anything, that means you did everything correctly. Woo, good job. But if you did, now you know kind of what to look out for, maybe where a gap in your understanding might be. So homework, quizzes, activities are really good things to look back on to study. Of course, there's this video, and then any notes and information you'll see in the PowerPoints, as well as the recorded lecture videos that you guys have access to. All of those are great tools to use. So without further ado, now I'm going to actually go over the study guide. The way that I like to have my study guides set up, the way that I would use study guides as a student was with each point, I would pretty much kind of go off on a little tangent talking about all the things I knew about that particular topic. So that's kind of going to be what I'm sharing today with you all here, as kind of a way to be on the lookout for what you need to ensure that you know. So we'll start with, of course, the categorical and quantitative variables, the definitions and examples. So a big point of knowing that I want you guys to be able to know the difference and be able to identify a categorical variable versus a quantitative variable. So think back to the first homework where you had that list of variables and it was like, oh, the amount of shopping carts in a store, or gender, or the different departments in a grocery store, deli, bakery, whatever. Those were all examples of different categorical or quantitative variables. So that's something that you can look back on as a kind of like, all right, what did we do? Or like, how can I study for this? Or what's one way? So knowing the difference, knowing when to differentiate between them. So for categorical variables, it's very much all or nothing. You either have blue eyes or brown eyes or green eyes. And if you have maybe a blue and a brown eye, or you have purple eyes, I don't know, that would be categorized as other. Everyone has to fit in a category with categorical variables. You know, you can be a psychology major, a biology major, computer science major. Those are all examples of groups of a categorical variable of college major. But the point is that you cannot be in more than one group. Otherwise, that's counting you as two people. The way that we measure categorical variables is by counting them. You know, how many people in the class have brown eyes? How many people are psych majors? How many people have, you know, how many people are their parents still married or ever were married? I don't know. But, you know, these are all categorical variables here that we're dealing with. And you either raise your hand or you don't. You either have brown eyes or you do not. So again, categorical variables are very all or nothing. Quantitative variables, my quick and dirty way to determine if you're looking at a quantitative variable and in turn a categorical variable is to ask, all right, can I find the average of this? Quantitative variables are typically measured numerically, so using numbers. So how tall are you? You know, your height in inches or centimeters or chickens. I don't know. How many chickens tall are you? Have you thought about that? But quantitative variables, again, measured numerically, and we can find the average of them. If I were to ask everyone in the class, how many siblings do you have? You would give me a number. If you're an only child, you would say 0. If you have one sibling, you would say 1. I only have one brother, so that would be me. I only have one sibling. And of course, however many siblings you have, oh, well, I have 4, I have 5, whatever. Those are all quantitative measures of number of siblings. And then again, to apply that quick and dirty method, if everyone in the class were to report to me or just to report how many siblings they had, well, we can find the average number of siblings that people have in our class, a quantitative measure, a quantitative variable. And then when we compare that to something like, oh, what college major are you? Psychology, biology, or computer science, or other, you know, if you're something that's not those, or if you're maybe a double major, or you have a minor, technically you're not only a psychology major if you're like a psych major with a child development minor or what have you. But anyway, so let's say those are our 4 groups. We have psychology, biology, not criminology, I'm sorry, I said computer science or other. All right, well, what's the average of psychology? You know, what's the average for other? It's like I don't know how to answer that question. What do you mean the average? If you compare that to, oh, I can take the total the number of siblings for each people in the class or the age of each person in the class or whatever. Quantitative variables, we can find the average. But then when you try to apply that to categorical, it's like, I don't know what you mean by finding the average of brown. I'm just going to count how many people have brown eyes or brown hair. That's what I'm going to do. So again, that's my quick and dirty way to determine if you're looking at a categorical or quantitative variable. And then when it comes to examples, while yes, this is a multiple choice exam. So when I say, oh, you should know some examples, that is not so much to say that, oh yeah, you'll need to write your examples in the exam because it's multiple choice. That's not the case at all. But rather having examples kind of, if you have a couple of examples for each a categorical and a quantitative variable in your head, it should be able to kind of provide you that standard, that basis of how you understand a categorical variable, how you understand a quantitative variable. So then when given new examples of those types, you can kind of maybe refer back to your own example and think, all right, is it kind of like that? Or is it kind of like my example I have for the other type of variable? So the examples is more so you can have that reference and kind of, it makes it easier for you to differentiate. If just the definition's all or nothing, quick and dirty, find an average, you need a little more than that. Okay. So for measures of central tendency, mean, median, and mode, when to use them and how to calculate. So I'll start with mean, excuse me. I'll start with mean. When do we use this? With most data sets. Mean, of course, is also known as the average, and we've already talked about finding average when we talk about our quick and dirty method of looking at quantitative variables. But for mean, we typically use this when we have a normal or close to normal distribution for our data, which tends to be a lot of the data that we work with in this particular class. We'll use mean a majority of the time as a measure of central tendency. Of course, with mean, we are also using this with quantitative variables, you know, number of siblings, the average age, etc. These are all variables that we can find mean for. Now, as far as how to calculate, of course, for that, we would just add all of the scores together, add all the number of siblings for each person in the class together, and divide by however many students there are in the class. So there you go. Median, we would use this when we have a skewed data set. So instead of it being roughly normal, you know, that bell curve we're really used to seeing, that's the normal distribution that's used for mean. For median, we are looking at more skewed distributions. So instead of having that kind of camel's hump where it's like, oh, kind of thin on the tails, and in the center, it starts to kind of just dome off, looking like a bell. A skewed distribution will kind of be something like this. I have my handy dandy whiteboard to draw it. I'm going to give a couple examples of skewed distributions here. So when we would use median is when the data set looks more like this. And actually, I'm going to stop sharing so you'll have a fuller view of this. So instead of it being better, like more kind of symmetrical, that's a poor drawing, but if this is our normal distribution where it's about the same on each side, you know, we don't have a leaning in one direction or another. These distributions do a lot. For this one, most of the data is on the higher end of the spectrum. We'll see a higher hump here, and the smaller the values get, the less and less and less they get. A lot of the data is focused on this side. And then over here, it's the reverse. A lot of the data is focused on this side, and it starts to kind of peter out as we go to the other end of the spectrum. For that skewed data, that is when using median would be the best measure of central tendency to use. Because as we know, mean is affected by outliers. The mean of 1, 2, 3, 4 and is going to be, you know, relatively small. But if we have the mean of 1, 2, 3, 4,000, that's going to be drastically altered. The mean is going to be drastically altered by outliers. Median is not. So if the median for 1, 2, 3, 4 and 1, 2, 3, 4,000 will still be the same. It'll be 2.5. We're looking at the middle position. So 1, 2, 3, 4 data points. Well, you know, we want to find the middle position. So between 2 and 3, we split the difference. 2.5 is in the center of those. That would be our median. Now, and with those skewed distributions that we have, where most of the data is on one end, and as we go to the other side, it starts to peter out. Well, there's those outliers are there. We have way more people on one side, and those outliers or in the outskirts of it, they'll be affected by those. So that is why we use median. And we'll see some examples of median will be like the population of cities in California, or the average income in the United States for people. There are certainly cities in California that are very large, like California, like Los Angeles, San Francisco, you know, those bigger cities. But we have a lot more small little cities in California, way more than we have these massive cities. You know, we have a lot of Centervilles, or just little, like, oh, you just turn left, and if you blink, you miss it kind of thing. We have way more of those cities because they don't require as much space, and people just kind of live. Maybe a city with a population of 1,000, we probably have a boatload of those in California. So we're going to have way more cities that have a small amount of people, and not as many cities that have massive amounts, like LA, San Francisco, etc. So that would be a skewed distribution. We would use median. Same concept goes for looking at average income. A majority of people make possible at an individual level, maybe not household income, but at an individual income, annual income, let's say, there's going to be a majority of people in this country that are, you know, probably making under $100,000 for one person in a year. Like each year they make $100,000 or less than $100,000. The majority of Americans have that. And of course, there's going to be those few and far between individuals who are making way more than that. You know, people who are making millions of dollars a year, even maybe billions. That's going to be a super small number of people there. But still, we have a very skewed distribution where a majority of people are kind of in the lower end of the income spectrum. And then a sparse few are in the upper, again, that upper 1%. There's a reason why they call it that, because there's not as many people there. So median would be another good way to calculate central tendency for a distribution of population of cities in California, or annual income. All right, and then mode, lastly, we use this when we are looking at categorical variables. So again, mode is just referring to the most. So I can ask, all right, the mode of major in this class is just saying which major has the most people. And it's probably going to be psychology. You know, psychology probably will have most of us in the class, or at least a majority of the class. will have psychology as their stated major. So the mode for this class in terms of college major would be psychology. It is the most. And this is a categorical variable. Same thing when we're looking at hair color. The mode for hair color, probably going to be brown. Brown is a dominant hair color. I haven't seen all of your hairs individually. You know, but ultimately I'm fairly confident in the fact that brown would be the mode for hair color in the class, or brown would be the mode for eye color in this class. And how we calculate that is simple as counting. Just how many people have brown hair in the class? Raise your hand or whatever. Like, okay. Now on to research methods in psychology. So I want to talk about these three: experimental methods, quasi, and correlational, also known as non-experimental methods. Experimental method, the first one, is where we can determine a cause and effect relationship. A key aspect of what makes it an experiment, as opposed to a quasi-experiment or a non-experiment or correlational, is that we have manipulated a variable. This is known as our independent variable. And with that manipulation, we are able to randomly assign our participants, our groups, the people that are in our experiment. We are randomly assigning them to be in that manipulated group or this one. An example would be, all right, let's say for this first exam, I flip a coin. That's random assignment. For each person in the class, I flip a coin. Every person, if you get heads, you get a study guide. If you get tails, you do not get a study guide for this first exam. Now, obviously, you watching this video, everyone has access to this video, so this isn't really happening. But again, let's just kind of roll with that idea. So I flip a coin, lands on heads, you get a study guide for the first exam. I flip a coin, you get tails, you don't get a study guide. That random assignment, that flipping a coin to where every person has a 50-50 chance to either get a study guide from me or not get a study guide from me, that is really what makes it an experiment. And that manipulation that's going on is, hey, it's the study guide. You either get one or you don't. I, as the researcher, am determining through a coin flip, through probability, but I am still determining something that is occurring to you. I am determining a manipulation in place, and I think that manipulation is going to cause a change in something else. I think that getting a study guide is going to cause you to perform better on exam 1. So there is a cause and effect relationship there. Study guides improve test scores. Study guides are responsible for increasing test scores. And I can test that by, again, just let's see how everyone did on that first exam. And I'm going to compare the two groups, the overall average of people who got the study guide versus people who did not. A quasi-experiment, we can still determine a cause and effect relationship. However, the strength of that cause and effect relationship is not as strong. Granted, there's no such thing as a perfect experiment. There's no such thing as a perfect research study in psychology. But as far as quasi-experimental is concerned, we don't have that coin flip I was talking about. We don't have people being randomly assigned to one group or another based on a coin flip. Rather, things with quasi-experimental, maybe we think that gender is going to cause, maybe we think that being a woman is going to cause you to have higher rates of depression. Okay, so there's a cause and effect relationship there. We have gender, men or women, and it's causing a change in your depression level. So our hypothesis is that women will have higher rates of depression. Now, when we're thinking of that variable, the thing we think is going to cause a change, it's gender. I can't flip a coin or randomly assign anyone to be one gender or another. I can't do that. You can't walk into my research lab as a woman. I flip a coin and say, haha, not today, you're non-binary. It doesn't work like that. You pretty much come in as you are. This is kind of a straightforward example for quasi-experiment, but I think it gets the point across. So I can still look at how, oh yeah, maybe women do have higher rates of depression, or maybe they don't. Maybe it's equal across the board for all genders. I don't know. I haven't done this study. But that would be a quasi-experimental study. If I am under the impression, if my hypothesis is stating, gender is going to cause people to have higher or lower rates of depression, that's my cause and effect relationship. However, without that random assignment, that coin flip, or just whatever it might be, I can't say for certain that causal relationship is not as strong as my previous example with study guides and exam score increases. Lastly, correlational studies, it is also known as non-experimental. There is nothing being manipulated here, not even looking at how there is no cause and effect relationship here. Rather, all of the data that we have is obtained through observational methods. So there is no manipulation. If I were to ask you, hey, report to me, tell me how many parking tickets have you received in the last year, let's say. And then also tell me how many times you took your driver's test. Okay. I haven't manipulated either of those. I'm not flipping a coin, and I'm not going to say, all right, well, you failed your driver's test 5 times. Or, oh, you got tails, so you only needed to take it once, you passed it your first time, so you've only taken it once, or whatever the case may be. No, I'm not doing that for correlational, for non-experimental. None of the variables are manipulated. I am observing what you are doing. I am observing what your responses are through no manipulation or control on my part as the researcher. I just take the data as it comes in. So when we have, maybe there is a relationship between how many times it took people to take their driver's test and pass, or just in general, maybe you never pass, I don't know. But how many times you have taken a driver's test, and then how many tickets that you have received, like parking tickets, maybe speeding tickets, whatever. Maybe there is a relationship. Maybe the more times it took people to pass their driver's test, maybe there's a correlation with the more tickets they might have. Or maybe it's reverse. Maybe the more times, the less tickets you have. I don't know. But correlational is looking at patterns of variables and how the patterns, they increase or decrease together or go in opposite directions. But it's important to note that we cannot say, oh, this, taking your driver's test more times caused you to get more tickets, or whatever that relationship might be. Non-experimental cannot use cause to explain the findings. It's more so, it's very kind of walking on eggshells, very careful language. It's saying things like, oh, well, as the number of times you took your driver's test increased, so too did the number of tickets you've received. Those two variables are increasing together. Now, we are not going to say that, oh, again, we can't say this variable is increasing because of that one. No, not for non-experimental, not for correlational. And that's because we haven't manipulated anything. With the study guides, comparing apples to apples, comparing the test scores for the study guide group and the no study guide group, we certainly can use cause because we have made that manipulation. We are comparing these two groups based on a manipulation we have done to see the clear cut and dry cause and effect results of it, not with correlational / non-experimental. Okay. Discrete and continuous variables. So rolling back, we can relate these to categorical and quantitative as well. Categorical variables can only be discrete. Discrete variables are kind of that same thing that categorical variables are. It's all or nothing. There's no in between. So if you think of a discrete variable, it can also be examples of categorical variables, like, oh, what was my examples from earlier? Oh, your hair color, that would be a discrete variable. Your eye color, a discrete variable. We're putting you in categories all or nothing. You're not a mix of them. You're not in multiple groups at once. It's very cut and dry, black and white kind of thing. Different streaming services you use, discrete variables. It is Netflix, or it is Disney Plus, or it is Paramount Plus, or whatever the case may be. There is no in between, which is in contrast, I should say, to continuous variables, which can be more on a spectrum. It can include decimals, let's say. So I can measure my height in inches. And if I am being precise with it, I can say, oh, I am 64 inches and a quarter. You know, I'm 5'4" and a quarter, 5'4.25, you know. Well, if it were discretely measured, I'd say, nuh-uh, you have to be either 5'4" or 5'5". You cannot be in between. You have to be one or the other. Well, that doesn't work for something like height. Or I know the example I believe I've used on a homework in the past was, you know, the distance from one place to another using Google Maps or something. Google Maps or like map apps or something will tell you, oh, your destination is 6.94 miles away or something. Again, it is a decimal. It is not 6. It is not quite 7. It's in between there. Continuous variables can do that. So quantitative variables are always, or quantitative variables can be continuous because, again, number of miles away doesn't have to be 6 or 7. It can be 6.94. So quantitative variables can be continuous, but quantitative variables can also be discrete. We can also have numbers. There is no decimals in our numbers. So for example, the number of siblings that you have, that is a discrete measure of a quantitative variable. You're not going to tell me you have 1.5 siblings. You might have a half brother or something, but that is more so in terms of familial relationship, like, oh, we have different dads or whatever the case might be. But that is still your sibling. That is one whole person. So if you say the number of siblings you have, you would say 1. Or the number of pets that you have. I assume you don't have half of a cat walking around your house, just 2 legs and meowing at nothing. I don't know. That'd be terrifying. I don't know. No, you have an entire cat. You have an entire bird or an entire dog. We don't measure the number of pets, the number of siblings we have, number of kids we have, things like that in continuous variables. Oh, I have a cat and a half. Or I have 2.6 dogs. Like, no, I have 3 dogs. I don't know why I would say it like that. Something like that. So again, but quantitative variables, I can find the average number of pets everyone has in the class, the average number of siblings, etc. But that's still a discrete measurement because there is no in between. There is no decimal when we're talking about like the number of pets that we have. So categorical variables can only be discrete, but quantitative variables can be discrete or continuous. Quantitative can be both. Alrighty. Next, we have measures of variability. So knowing how to compute them, you won't need a calculator for the exam, but you still will need to know how to calculate these. So there might be an example of, oh, you know, here's an example of someone doing a population standard deviation calculation. Did they do it right? So you might have to recognize it or do a quick calculation of it. But anytime that I ask you to calculate standard deviation or variance by hand, it's going to be very minimal. You'll maybe have just a couple of values. But off the top of my head, that should not be an issue. So measures of variability, we have range, variance, and standard deviation. So I really want to know what these are telling you guys as well. So range, that's just taking the biggest minus the smallest. As far as our measures of variability is concerned, it is the least involved. Again, we're only looking at 2 values here for range. That's it. That's it. Just 2. The biggest and the smallest. And then that's the span that our data is. So yeah, it measures dispersion, but not nearly as in depth as variance and in turn standard deviation. So variance and standard deviation are looking at how far the scores are dispersed from the mean, not just the biggest and the smallest score. No, they're looking at how every score deviates, how far it is from the mean. For variance, it happens to be the squared scores, because when we calculate variance, we subtract the mean from each individual score in the data set. We take those differences and square them and add them all together and then divide by either our population size if we're doing population variance, or divide by our sample size -1 if we're doing sample variance. But ultimately, we're squaring everything. And so it's kind of a bloated number. So technically, variance is the measure of dispersion of squared scores and how far those squared scores deviate from the mean. But we're not always the scores that we have, like, oh, I have one sibling, I have two siblings. Let's say we take our variance and standard deviation for, let's see, we check the dispersion for number of siblings that people have in this class. Well, we don't, yeah, like we calculate variance to get that variability. We need to square it. Otherwise, if we don't, it will always equal zero. And we know that a variability equal to zero means all of the scores are the same. There is no variability, but that's not true. So that's why we square variance. It has to be done. Just mathematically, it'll always equal zero if we don't. But with that being a necessity of what we have to do of squaring them, well, standard deviation is our way to kind of right the ship, kind of trim the fat a little bit, kind of cut down on the bloat, because we don't need them squared, at least in terms of when we're reading the variability. Oh, I have a variance of 75 or something. I'm like, oh my goodness, that is, but the biggest score here was 20. What do you mean we have a variance of 75? Oh, that's approximately how far the squared scores deviate from the mean of 7, or I don't know, whatever it might be. Oh, okay, it's 75, doesn't make sense. Standard deviation, we're kind of trimming that. So standard deviation is still measuring the dispersion of scores from a mean, but this is the scores themselves, not these squared scores like we did for variance. But now it's like, all right, let's look at the scores in the raw here. So to kind of remove that bloat, we square root the variance to find standard deviation. Essentially, we're canceling out all that squaring we did before, but in doing so, we're not left with zero. We still have a measure of variability of dispersion. So again, one good thing to keep in mind for variance and standard deviation is that the closer to zero that it gets, the less spread there is, the less dispersion there is within a data set. So a data set that has a standard deviation of 20 is going to be a lot more spread out, kind of spread across the distance of the mean and along the lines, like on the outskirts, or just not as closely huddled to the mean as, let's say, a data set that has a standard deviation of 2. There's going to be a lot less dispersion in that 2 standard deviation data set, because the smaller the standard deviation gets, the less, again, spread out that data is. Okay. So next, properties of a normal distribution, including the empirical rule. So we have some basics as far as properties of a normal distribution. We know that it is always symmetrical. This is what looks like the bell curve. The normal distribution is what we're going to use in the background for. It's kind of our bread and butter of how, after this first exam, how we make our conclusions using the tests we're going to learn after this first exam. I like to use the example of, well, actually, no, I'll talk about that when I get to it. I'm jumping ahead. I apologize. But for properties of a normal distribution, including the empirical rule. Well, first off, the normal distribution itself is this theoretical la-la land for statistics. Most data that we come across, number of siblings in a class of 40, the average age of Fresno State students, or whatever the data is that we're looking at, the distribution of it, again, if we were to like graph that and see what it looks like on like a number line and draw for how close together all the scores are, just, that bell curve, our data isn't always going to look like a bell curve, but we assume it will for sake of simplicity and for drawing our conclusions, for generalizing our populations using just a sample. Okay, so with that, the normal distribution can have any positive or negative value for the mean, median, and mode. So all 3 of those measures of central tendency are in the center, in the middle. The area under a normal distribution is always 1. It's equal to 1. The standard deviation is always going to be positive. And we know this because if we can't have a negative standard deviation, because 0 means everything is the same. And if standard deviation is a measure of how different all the scores are, how far apart, how dispersed the scores are, well, 0 meaning all the same, you can't get more same than same. So we can't have a negative standard deviation when 0 is the least deviated it can possibly be. Everything is equal. Anywho, so The empirical rule. Oh, and we also know for normal distributions that the tails are asymptotic. And that just means that when we draw that normal distribution, it typically has an endpoint, right? But mathematically, technically, those tails will never touch the x-axis, that horizontal line that we draw it on. Technically, those, as we go further and further from the center, getting to those tails where it's just like slivers and slivers and slivers and slivers, they never technically touch the x-axis. That is, again, referred to as them being asymptotic. Now, the empirical rule is stating that in a normal distribution, from the mean, 68% of the data will be one standard deviation above and below the mean. So between that standard deviation above and below the mean in that area, 68% of the data will fall there. And then 2 standard deviations above and below the mean, 95% of the data will be there. And then going 1 standard deviation further in each direction, 3 standard deviations above and below the mean will have 99.7% of the data there. That's the empirical rule. And the empirical rule is something, again, that we will use for in the future when we start concluding making conclusions with our inferential tests, again, after the first exam. Okay. Now, the difference between theoretical and experimental sampling and how to calculate it. So first off, what are some of the basics? Well, theoretical sampling is used when we are talking about statistical theory, when we're talking about the sampling distribution of the means, which I'll talk about in the next bullet point for characteristics of the means. Of sample means. But the theoretical sampling method is just determining, given a particular population size and sample size, how many total possible samples can we have using theoretical methods. So how many samples would there be in a sampling distribution of the means? It uses theoretical sampling. Now for theoretical, here, I'm going to have to use my full screen again. For theoretical, the formula we would use to calculate that, in fact, let me actually write that. Theoretical is capital N to the power of little n, or population size to the power of the sample size. So I might give you, like, very similar to the homework that we had, I might give you a population size of 5 and a sample size of 2. And I might ask, how many total possible samples are there using the theoretical sampling method? Well, all you would have to do is, given this information, I'm always going to give you that information if I ask you that question. Okay, I'll just plug it in. So 5, which is my population size. So 5 to the sample size power, so 5 to the second power, 5 squared. Oh, that equals 25. 5 times 5. Perfect. Alrighty. Now, theoretical sampling methods, there's also a couple things to keep in mind. First off, theoretical always uses sampling with replacement. And it also matters in terms of the order that participants were selected for the sample. I like to use the example of like a basketball team. So if you're going to be playing like a pickup game of basketball, and let's say that, it's like, all right, we got 2 team captains and you get to choose who's on your team, Theoretical sampling methods, you're never going to play a game of basketball. You're never going to do it because you can pick, let's say I'm first team captain and I'm picking theoretical samples. I'm picking my theoretical team. And all right, I want LeBron James. All right, he's on my team. But remember, with theoretical, it's sampling with replacement. So in this example, that would mean, okay, LeBron James is on my team. Okay, now I put him back in the, back in the draft. I don't get to keep him on my team, but rather I'm replacing him, sampling with replacement. So now I can select him again I can pick LeBron James, LeBron James. Heck, if I have a team of three, I can pick him 3 times using theoretical sampling methods. I can also the order of picking samples matters. So or picking participants for my sample matters. So if let's say I pick LeBron James first, Steph Curry second, and then Damian Lillard third, these professional basketball players. If I pick them in that order, James, Curry, Lillard, well, with the order mattering, if I were to pick Lillard first and then LeBron James and then Steph Curry, that would be a completely different team. Even though it's the same players, I pick them in a different order. I pick Damian Lillard first instead of LeBron James first. So that's a different sample according to theoretical sampling methods. And again, we use that when we're making our when we are I can't write and talk at the same time. We use theoretical sampling methods for the theoretical aspect of statistics. So when we are comparing things using that sampling distribution of the means, it's very statistical theory. We assume that the data that we have follows that normal distribution close enough to where we can use it, etc. Very statistical la land, very, when I grow up, I want to be a normal distribution kind of thing for statistics. Now, experimental sampling methods are the opposite, or at least where the theoretical sampling methods, it's like, all right, the order matters and we can pick people multiple times, sampling with replacement, but we use that in theory. In practice, we use experimental sampling methods. And using that same analogy that I used for picking a basketball team, this is what we did as kids, or maybe you're still playing pickup games of basketball or dodgeball now. I don't know. But you have 2 team captains, or you have a team captain and it's like, all right, I want LeBron James. Now he's on my team. The other team captain's like, damn, LeBron. All right, well, then I'll take Steph Curry. Damn it, I wanted Steph Curry. All right, I'll take Damian Lillard. Damn it, I wanted him. Or like, whatever. We don't put our players back into the draft. Same thing for experimental sampling methods. We do not sample with replacement. It is sampling without replacement. So the participants we choose for our sample, they stay in our sample, and we cannot pick them more than once. We can only have LeBron James once. We can't have a team of 3 LeBron Jameses using experimental sampling methods. Theoretical, we can. Oh, my cat just opened my window coming out of it. Hello, Petunia. But experimental, we can't. We can only have LeBron James once. And then when the order matters for theoretical, remember the team of LeBron James, Steph Curry, and Damian Lillard is different than the team of Damian Lillard, LeBron James, Steph Curry, a different order. Ooh, it's a different team. No, in experimental sampling methods, it's like, no, I still have those same 3 players of James, Curry, and Lillard. So I still have a pretty awesome team going on right here. Doesn't matter which order I pick them in our little make-believe draft here. They're still all on my team. They're still on the, Fresno Cooper Stats team. I guess that's the name of my basketball team. Pretty poor. No one's going to want to come to the Fresno Cooper Stats. But ultimately, experimental sampling methods follows what we would actually do in like real life. And then the formula is using factorials. So this is the formula. The N, population size. And it'll always look so exciting. But factorials for a lot of students are like terrifying because we put exclamation points in math now. What the heck is going on? But ultimately, that is saying, I'm going to simplify it here. So I'm going to plug in using that same, using the examples I have, my example on the board here. I'm plugging it in like this. So 5 factorial divided by 2 factorial times the factorial of 5 minus 2. So I got to do that parenthesis first. So it'll be simplifying it 5 factorial divided by 2 factorial times 3 factorial. That. Okay. And then to calculate that, All I'm doing is for the factorials, I am multiplying by a sequential counting up to 5 or a sequential counting up to 2 or to 3. So the factorial for 5 will be 5 times 4 times 3 times 2 times 1. Again, if I were to count to 5 starting at 1, I'm just multiplying all of those numbers together. And I would do the same for any factorial. So for the 2 factorial, it is 2 times 1. And for the 3 factorial, it is 3 times 2 times 1. So I would do that. And according to this, these are going to cancel out. Those are going to cancel out. So I can just simplify it to, all right, 5 times 4 is 20. And then 2 times 1 is 2. So divided by 2. Oh, 20 divided by 2 is 10. Using experimental sampling methods, I will have 10 total possible samples given a population size of 5 and a sample size of 2. Also notice that theoretical sampling methods are always going to have a larger number of samples, possible samples, in comparison to using those exact same numbers for experimental methods. And it makes sense. Again, if James, Curry, and Lillard is a completely different team than Lillard, Curry, and James, like if those are two separate teams, or if I can have one team be LeBron, a separate team being Lillard, that's a hard one to say quickly, and another completely separate team to be Curry. Of course, theoretical is going to have more samples. It's going to have more because, practically using the experimental side, it's like, I can't have 3 LeBron James on my team. He's only one man. Like, I only get him once. Like, what do you mean I get to have him 3 times? So it always makes sense that the experimental method is going to have less total possible samples than theoretical. Okay. I'm trying not to make this video too long, so I apologize. So going a little quickly now, as far as characteristics of the sample mean, for these, I know that the sample mean is a little more complicated. That sampling distribution of the means is much more complicated. Again, this is diving deeper into statistical theory. So what I like to say is that we use the sampling distribution of the means. If our population is our perfect cake that we see in a recipe book, it's like, I want to make that. And our sample that we gather to make that cake, that is our ingredients. So I want to make that cake. I am going to get eggs, flour, sugar, etc. I want to know what the Fresno State population thinks about something. I'm going to take a sample of 40 students and use them to generalize. They're my eggs and bread. And you don't have bread in a cake, but butter, whatever. However, you can't just have flour, sugar, and eggs and then be like, ooh, delicious cake. Can't wait to eat it. It's gross. You need to do something to it. You need something. You can't go from eggs to sugar and flour to look at this beautifully iced cake. It's gorgeous. And oh, it's, nice and dense or moist or whatever. No, you need something. You need something in between that raw state of the dough or the batter and the baked delicious cake itself, and that is an oven heat. So imagine if we are using samples to generalize to a population, we do use samples to generalize to a population. Imagine the sampling distribution of the means to be the oven. We have the ingredients, we have our sample, we know what we want to see, we know we have this the cake, that's what we want. We want to represent this, but we can't just crack a couple eggs in a bowl and say, look at this delicious cake I made. No, we need to bake it. We need that kind of filter, that go-between. That's the sampling distribution of the means in a nutshell, or in an eggshell, I should say. Anyway, so when it comes to characteristics of the sample means, as far as these 3 basic factors, they're going to be pretty straightforward. So we have an unbiased estimator. That is, on average, all the sample means that are in the sampling distribution of the means is going to be equal to the population. The average of all those averages we see in the sampling distribution of the means equals the population mean. The central limit theorem is saying no matter how wonky our population might be, remember when we were talking about the different distributions that we can use for median, how they're skewed in one direction or another, where a lot of the data is over there, a lot of the data is over there. Well, according to that, that skew, if our population looks like that, let's say it's skewed, or let's say it is normal, or our population, regardless of what the population looks like, skewed or normal or anything in between, the sampling distribution of the means will always be normal. It will always follow the empirical rule. It will always be symmetrical, and all of those properties we talked about for normal distributions, the sampling distribution of the means will always be that way. Doesn't matter what the population looks like. It's always perfect. Again, it's always wonderful and it's always beautiful and nothing hurt. Minimum variance means that, hey, if you are going to gather your samples, all the samples that you're going to have in your sampling distribution of the means, if all of them are going to be there, I guarantee you, if they're going to be derived from the population, which they are, I'm pretty sure you're going to have some variability. Minimum variance just means bet at least one person's going to be different. I bet not every single person in, not every single student at Fresno State has the same number of siblings. I bet that there's going to be some variability. There's going to be some variance there. So minimum variance is just saying, hey, not everyone in the population is going to be equal. Not everyone's going to have the same number of siblings. Not everyone's going to be the same age or whatever it is that we're measuring there. So there's going to be some differences, some variability. Describing the difference between standard deviation and standard error. Well, standard deviation is measuring we've talked about standard deviation a lot already. So that we use for populations and samples. Standard error is what we use for sampling distribution of the means. It's still measuring something very similar, the dispersion within our sampling distribution. However, instead of to see how each individual score deviates from the mean, like it is for standard deviation, standard error is saying how far each of these groups of 40 or groups of 60, whatever our sample size is, the average of each of those groups, how far they are from the true population mean in the center. That's standard error. Very similar though, the smaller our standard error is, the closer to zero it gets, the less variability there is within our sampling distribution of the means. The closer and closer our data is to possibly being the true population, being a good representation of what the population actually is. Okay. Calculating and interpreting z-scores. You won't need a calculator. As far as exams are concerned, I like to use pretty straightforward numbers. So it might be like, I'll give you information for the z-scores and be like, oh, your population is 4, the X value is 2, or the mean is 4, the value I want you to calculate is 2, and the standard deviation is 1 or something. And again, this is an open note test, so you can have those formulas at your side. You don't have to memorize them. I don't care if you memorize formulas. You guys, any monkey could do that. But rather, I want you guys to be able to calculate those probabilities. So using z-tables. Another point is you can use the z-table if you're more comfortable using that as far as the one we have. But in terms of when I say a z-table is not needed, for questions that you would need to find the probability using a z-table, in that question on the exam, I include like a little excerpt, a little portion of the z-table. So instead of having to try to find the z-score in this massive thing, I give you a couple of different z-scores and their respective B and C columns, the probabilities in those columns, and then I work with that. So, and then, you were able to do that. Understanding the difference between populations and samples. So populations, you have access, you don't have to generalize. It's not a portion, it's the whole pie. It's not just a slice. When we're reading our problems, if we're saying, oh, I want to know about how college students feel about potatoes, whatever. Okay, my population is college students there. I want to know about this particular group of people. How do college students feel about potatoes? And a sample, if I were to say, I took a group of 60 college students to find out how they feel about potatoes. Well, if I'm not saying anything more specific about college students, as far as my population was concerned, that initial group I was interested in, it's not saying like, oh, college students in California or college students in this class of 60, and I took all 60 of them. I'm not saying that. So this group of 60 that I have to assume they are representing all college students across the country, across the world. I don't know. But 60 is certainly not representative of the entire population. So that by default would be a sample. So you just got to read the question carefully. Is the number you're getting, oh, I want to know, let's say I am interested in seeing how my stats class did, my online stats class did on their first exam. I am only interested in my online stats class and how they did. I don't care about other Psych 42 classes. I don't care about how Math 42 did on their first exam. I don't care. I'm only focused on my online stats class. That's my population. That's the group I'm interested in. And I can look at all of your scores and you would be my population. Boom, bam. Now, lastly, understanding the difference between inferential and descriptive statistics. I like to use the example of descriptive statistics as just what the data looks like. That would be its central tendency, mean, median, and mode. That would be its variability, your range, your variance, your standard deviation. Tables and graphs can also be used for this. But I like to use like the more human example of descriptive statistics is what the data looks like. So right now I am wearing a sweatshirt. I am wearing a beanie. I am wearing pants, but you can't see them. You're welcome. I am wearing pants, but that is just what I look like. You can't tell too much about an individual just by what they look like on the surface. Just like you can't really tell the relationship that variables have with one another just by looking at their mean and standard deviation. That's where inferential statistics comes in. Inferential statistics is where we look at those relationships. Is there a cause and effect relationship here, like we talked about for experimental studies? Is there a pattern of change between these two variables like we looked at for non-experimental / correlational studies? What is the relationship here between study guides and test scores that I can't necessarily just tell by looking at a mean and standard deviation? I got to go a step further and use the oven to turn my eggs and ingredients into the cake. I have to take a sample to represent a population, and the oven, part of the oven temperature of using the sampling distribution of the means is also where I'm going to plug into my inferential statistics there. So this is where we're looking at the relationships, causal or not. Now, in comparison to my human example, where me wearing a sweatshirt and a beanie is descriptive statistics, inferential statistics would be things you can't just necessarily see on the surface. So am I an asshole? You can't just tell by this Morro Bay sweater I'm wearing. You would have to go a step further, do some analysis. Don't ask my therapist. You don't need to know if he thinks I'm an asshole or not. Probably does. No, I don't care. Anyway, so absolutely. So inferential statistics, we're going a step further. We're digging beneath the surface. It's not only just, oh, I have a bigger mean here, so that must mean it's bigger. No, let's really look at let's use some theories here. Let's actually apply statistics and answer those questions. All right. And with all of that being said, that is the video for the study guide. So if you have any questions, reach out to me. I will post an announcement when the exam is live. And within that announcement, you will also see how long you'll have to take it, the duration. I'll pretty much remind you of this information that I've given at the beginning of this video. But good luck to you all, and have a great rest of your day.